Okay, today let's learn how to assign oxidation numbers. Oxidation numbers are theoretical things. They're very similar to ion charges that we used when we learned how to write formulas for ionic compounds. However, oxidation numbers occur for all compounds, whether they're ionic or covalent. An oxidation number is based on that atom's valence electrons. If an atom has 7 valence electrons, for example, then it can have an oxidation number ranging in from the maximum of losing all 7 electrons to be plus 7, or to the minimum of gaining 1 electron to complete its octet to negative 1. So all atoms have a range of oxidation numbers possible based on their valence electrons. Let's do another one to illustrate that. Let's pick carbon. Carbon has 4 valence electrons. So when it bonds, it can either lose those 4 and have an oxidation number of plus 4, or it could gain 4 to complete the octet and have an oxidation number of minus 4. So a carbon atom can have an oxidation number anywhere from positive 4 to negative 4, including partial charges, which would be more advanced, and we don't really see those in high school chemistry. Here we see some rules for finding the oxidation numbers of atoms in a compound. Let's look first of all at rule number 1. Free elements are assigned an oxidation number of 0. I know in these examples here, they showed us two diatomic molecules, and sulfur, molecular sulfur. Then there was also an atom of iron. Let me summarize that a little bit more simply. If an element is on the periodic table, its oxidation number is 0 as a neutral atom. Also, what we're saying here is that the diatomic molecules, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all those we learned in pre-AP chemistry, that diatomic state is their natural state, so their oxidation number is 0. And then some elements will have that, like sulfur you see here is S8. That's its normal state. That's when it's 0. Some other examples would be phosphorus, which comes in little groups of 4. Its oxidation number is 0 there. And there would be some other ones, but you really won't ever see those in high school chemistry either. So that's rule number 1. Rule number 2, the alkali metals always have an oxidation number of plus 1. So this is sodium, potassium, lithium, rubidium, cesium. These guys only have 1 valence electron, and that is so close to 0, to losing it. Their electronegativity values are so low that that's really all they'll ever do. And then the alkaline earth metals in group 2, that's calcium, magnesium, barium, strontium, they only have 2 valence electrons, so they really want to lose those 2. And they'll only form plus 2, and that's all they ever do. So we have a lot of confidence in knowing what the alkaline metals and the alkaline earth metals do. The next rule tells us about fluorine. Fluorine in compounds is always negative 1. And in pre-AP, I told you that the reason for that is fluorine is always the boss. Fluorine is the most electronegative element on the periodic table. It wants to gain 1 electron to complete its octet. It will always do that, no matter what. And then we have the rule for hydrogen. The hydrogen rule tells us that hydrogen can be one of 2 things. Because hydrogen has 1 valence electron, if it bonds with a metal, hydrogen will be the most electronegative and be negative 1. So remember, hydrogen's electronegativity value is about 2.1, which is moderately high. So when it bonds with metals, it's the boss. It'll gain that electron to complete the first ring octet of 2 electrons, and hydrogen will be -1. But when hydrogen bonds with most nonmetals, it is no longer the boss because it's not quite the most electronegative, and when it bonds with nonmetals, it'll have an oxidation number of +1. So we don't always know what hydrogen's going to do, but we have a pretty good idea based on what it's bonding with. Then, the element that we almost always look to get started is oxygen, because oxygen is 99% of the time going to be -2. Oxygen is the second most electronegative element on the periodic table. It's almost always the boss, and it wants to gain 2 electrons to complete its octet, so it will do so. The only element that can boss oxygen around is fluorine. So when oxygen bonds with fluorine, it will not be -2. And then oxygen can also do some strange things like peroxides and superoxides that we'll talk about when we come to them. Then the rule for finding oxidation numbers is kind of stated in number 6. The sum of the oxidation numbers of all the atoms in a species must equal to the net charge on the species. So, for example, in the element Fe, the net charge is 0, so the oxidation number is 0. Another example, something very simple, calcium oxide. This is a neutral compound. Its total charge is 0. So oxygen has an oxidation number of -2, charge -2. So calcium has to be +2 because those two numbers have to cancel in a neutral compound. We would do the same kind of thing for cations or anions, but we just have to look at their charge. If, for example, if we use nitrate, NO3 -1, when we add up the oxidation number for oxygen and the oxidation number for nitrogen, they're not going to equal 0, they're going to equal -1. We have to take that into consideration. Okay, let's do some examples. Let's start out with an old favorite, carbon dioxide. Now we want to find the oxidation number for each element, the carbon and the oxygen. So the first thing we do, and this is a sort of a Taylor rule of thumb, is identify the most electronegative element out of the compound. Now if you've forgotten how to do that, remember fluorine is the most, oxygen is the second. And as you go left across the periodic table toward the alkali metals, electronegativities are going to decrease, and as you go down the periodic table, they're going to decrease. So the most electronegative stuff is up in that top right-hand corner of the periodic table: fluorine, oxygen, chlorine, nitrogen. Don't count the noble gases; their oxidation number is 0, or their electronegativity is 0. So we're going to start with oxygen because we know its electronegativity is higher than carbon's. So we'll use the rule that when oxygen's the boss, its oxidation number is -2. Now, we talked about carbon earlier. Carbon is at the mercy of oxygen now, and it can have an oxidation number anywhere from +4 to -4. We just have to figure that out. So we'll use a little algebra. We'll say that X for carbon's oxidation number, and there's only one of them, plus there are 2 oxygen atoms that each have an oxidation number of -2. And the rule number 6 that we looked at before says the sum of these have to equal the total charge. Well, CO2 is a neutral compound. The total charge is 0. So we'll solve for X. X minus 4 equals 0. So we then know that X is equal to +4 for carbon. That's its oxidation number. Let's do another. Let's do sulfate, the polyatomic ion. Again, sulfur and oxygen. Oxygen is the boss. So we know that oxygen is -2 charge. Its oxidation number is -2. And sulfur with 6 valence electrons can be anything from +6 to -2. So let's find out which it's going to be. So the same kind of algebra, there's one sulfur, and there are 4 oxygens that are each -2. And this time they are not going to add up to 0, they're going to add up to -2 because we're told we have this charge. So let's do the algebra. X minus 8 equals -2, X equals +6. So in this case, sulfur is +6. And the way we report that, I didn't do it for the last one, but we would just say sulfur is +6 and oxygen is -2. Nothing real fancy there. So here's another example with this time 3 elements. You could do this a couple of different ways. I'm going to do it with all 3 elements at once just to show you this particular method. So the same rules, let's find the most electronegative element. It's going to be oxygen again. So we know what oxygen is going to do. The rule number 2 also told us that we always know what calcium is going to do. As an alkaline earth metal, it will always be +2. Nitrogen, on the other hand, with 5 valence electrons, can be anywhere from +5 to -3. So let's find out what it's going to be. So we have 1 calcium atom, and then we have, be careful with this, we have 2 nitrogens that are X, and then we have 6 oxygens that are each -2. And this time it adds up to 0. There was no charge shown here. So do some algebra. 2 plus 2x minus 8 equals 0. I'm going to allow you to do this sort of in your head. We'll carry the 8 over and take 2 away, so that equals +6. And then we'll divide by 2. X equals +3. So in this case, nitrogen is +3. Well, I was just kidding. I know better than that, so I know I screwed up somewhere, and I know where that is. It's all in the math. So let's do some algebra again. What do you say? How about 2 plus 2x minus 12 equals 0. Okay, 2x equals 10, and x equals 5. I knew that was supposed to be the answer, so when I saw 3, I had a mild heart attack. But nitrogen in this case is 5. Okay, so hopefully that's a good reminder on how to find oxidation numbers. We're going to practice in class. Just remember your rules, and remember to find that most electronegative element, and let that be the starting place for assigning your oxidation number. The most electronegative element is the boss. It will fill its octet up and do whatever it takes to get that done, and then go bank on your alkali metals or alkaline earth metals. And for all those intermediate elements, assign it to X and use the algebra to figure out what the oxidation number is. So let me know in class if you have any questions, and we'll work on it more together.